Welcome to the fourth assembler lecture. In this lecture, we're going to do some interesting instructions that are a lot more assembler-like, if you will. I mean, we've obviously done things like addition and subtraction since you started programming, whereas the type of operations I'm going to go through in this lecture, though accessible via a higher level language like C or C++, it's far more relevant in an assembler context, and it makes sense with the type of efficient operations we wish to actually perform. So we're going to focus on bit operations in today's lecture. Now, obviously, a bit is kind of the fundamental building block of any computer system. Generally, we use it to mean true or false, and sometimes we'll have a sequence of bits which we use to represent something slightly more complicated. So if, say, for example, I wanted to uniquely identify a location on a chessboard, there are 64 blocks in a chessboard, and actually I could uniquely identify which block a given piece is in on the chessboard by simply using 6 bits. That would be sufficient because 2 to the 6 is 64, which means that with a small amount of bits we can actually get a lot of representational power. Okay, and that's the general trend with bits, in the sense that though it's a simple encoding like any number, the way in which we use it can be powerful. We can use specific combinations of the bit string to represent many specific things. Now, actually, in the realm of optimization, a lot of combinatorial optimization problems are recast to simply be binary optimization problems. So it comes up in a lot of context. So what bit operations do we have available to us? Well, the first thing is to perhaps distinguish between two types of bit operations. So you get bit operations that can work on individual bits, and that's very much in line with the type of operation that you've encountered, and they're often referred to as logical operations instead of bit operations. So that's your typical example where you'll say, for example, true and true, which ends up being 1, true and false, which ends up being 0. In a language like C or C++, we denote this kind of logical bit operation using the double ampersand for and this double bar for an OR operation. However, we're actually more interested in the generalized version of this operation. So instead of working on 2 Boolean values, we rather work on 2 bit strings. So you'll see here we have an example where we have a left bit string and a right bit string. And by using this AND operation in C or C++, we are actually performing the logical operation at a bit level. So I'm basically performing an AND between this element and storing the result over here. And now I repeat that for each of the extra bits. So I will then take this bit and AND it with this bit, and as a result I'll set the second bit in my resulting bit string. And this is referred to as a bitwise operation. And in C and C++, you engage this by just using an AND. Okay, as opposed to the double ampersand sign, you just use a single ampersand. And here we have the same idea with bitwise OR, where we use a single bar to indicate a bitwise OR operation, where I'll actually take the OR of each component from the left bit string and the right bit string. So again, I'll, for example, be ORing this 0 with that 0 and putting the result into this bit. I'll be ORing this 0 over here with that 1, and therefore I get a 1 over here. So in essence, it's a extension of the logical operation. We just do it across a whole bit string instead of just using 2 binary numbers. Now, it is possible in assembler to actually directly set and reset bits, and in many situations to actually test what a specific bit is, but by and large we're going to focus on these bit operations that are called bitwise operations, where I actually work on whole bit strings as opposed to just a singular bit. So what kind of operations do we have at our disposal? So let's start with the simplest of those, which is the NOT operation. In C++, we indicate a logical NOT, so this is basically one that only works on 1 Boolean value, using the exclamation mark, which I'm sure you've encountered many times. But if we want to perform the bitwise NOT, so if I want to negate each and every bit in my bit string, what I do is I use this tilde. Okay, and that will negate each of the bits in my whole bit string. So let's just look at some kind of practical examples. Everything that I write here is kind of true in the context of C++, but it is a good indication of what's actually happening. And there's a lot of surprises that I think some people miss with the way in which C and C++ treat these binary numbers. So the first two is pretty straightforward. If I take the negation of 0, so not false, I get a true. If I negate 1, I get a 0. So that's pretty in line. Same thing applies if you use the kind of reserved word of your language, that if I negate false, I get true, even if I'm using the bitwise version, because this corresponds to a singular bit, so it obviously does the corresponding appropriate flip. What's more interesting is if I do a bitwise, say for example, across this binary string, you'll see what happens is I negate each bit. So you'll see this first one becomes a 0, this next 0 becomes a 1, and so on across the whole bit string. Just because you will see this being done in the context of hexadecimal numbers, it pays to look at this example. You'll see here that if I take the not operation, the bitwise not operation, across the hexadecimal value FF00, I end up getting 00FF. Now, the reason that happens is that F corresponds to the nibble or the hexad 111, and if I take the if I simply not those bits, I end up getting 0000, and the same thing applies, that these 0 hex values correspond to 000, and if I flip them, I end up getting 1111. So my zeros become Fs and my Fs become 0. Now, something that you may actually not be completely familiar with in the context of comparisons, and particularly in the context of C and C++, if, for example, I make a comparison between two values, the way in which it's evaluated is maybe not in line with what you'd expect. If, for example, I take the negation of the value 1,000, well, in this case I think it's a million, that actually is equal to 0, or more specifically, it's equal to not. So in C and C++, any non-zero integer is seen as true in C and C++. It's actually a bit of a weird feature of C++, because it's the manner in which it handles conditional statements is that it actually is capable of working with ints as opposed to just Boolean numbers, which is why you get that behavior. It also means if I have a statement like this, if 5 and then some content, this loop or this if statement body will always be executed because a non-zero value is treated as true. So it's a little bit of a quirk of the language. Now, these remaining two are quite interesting. So imagine you're doing this in C++ and you have the value 0, and assume these are signed integers and this is stored in a variable, and I apply the bitwise not to it. Okay, so I apply a bitwise not to 0. Now, the question is, what number would that actually be after I've applied the bitwise not? So what would it equal to? The same thing applies to if I were to take the negation or the bitwise not of the number 1. What value would I get? So I want you to pause the video here and try and figure out what they would be, and actually see if you can actually get to the right answer. It will be quite likely that it will be a bit of a surprise to you. So this is what they evaluate to. So bitwise not of 0 is equal to -1, and I'm assuming for most of you that will be a little bit of a surprise, but if you think it out, it actually makes perfect sense. Now, in C++, if we were working with, say, an int, it would be 32 bits, but just for the sake of this example, let's say our integer was only 16 bits. So if I write out 0, okay, so I'm writing out 16 zeros in this context, so it's a very, very long number. This would be 32 bits if this was an int, obviously, but for the sake of demonstration. Now, what's happening here is when I apply this bitwise negation across everything, is obviously all of the zeros become 1s. And now you have to ask yourself, what number does this actually represent? So integers are always stored, or at least signed integers are always stored in 2's complement form, which actually means that this is a negative number because it has a leading 1. So what's the number that it actually represents? If I were to see out this to a screen, what would I get? Well, because I know it's in 2's complement, how do I get back to the actual posit or the actual number? Well, all I have to do is I have to flip all of the bits. So I go back to zeros everywhere and I add 1, which is why I'd end up getting the value of -1. So I obviously have a 1 here after I did the 2's complement conversion, but this number over here, which what we got after the negation, or the bitwise negation, is simply -1. Same idea applies for -2 when I take the bitwise negation of 1. So maybe also work through that example yourself just to see that you can get to -2. So there's a lot of interesting behavior that we can encounter. So there's a lot of things to always be kind of on your toes with bitwise operations, because there's a lot of tricks that make calculations potentially faster, but it does sometimes rely on some nuances of bitwise manipulation. So how do I perform a NOT operation in assembler? Well, I have a straightforward instruction called NOT, and it takes a singular operand, and what it does is it simply flips all the bits, or in a more familiar terminology, we say it performs the 1's complement, but in essence, it just flips all of the bits. Now, this is something that I think is important to distinguish, is that NOT is a 1's complement, and neg is in essence a 2's complement, because neg actually makes the number negative, whereas NOT does not. So it's just something to keep in mind. They do not actually do the same thing. The NOT operator doesn't affect any flags. If you remember from the last lecture, we have things like sign flags and 0 flags that can get set when I add numbers. No flags are affected in the context of the NOT operator. And how do I actually use this? Very straightforward. I simply use the instruction NOT followed by my 1 operand. This operand can either be, well, the operand first I should say is the source and the destination. So what will happen is I will NOT every bit in RAX and store the result back in RAX. And what I'm allowed to actually pass through to NOT is quite straightforward, in that I can either use a register or I can use memory. I can take the NOT of either a register or a memory, but if I'm going to NOT directly into memory, obviously if I just had a statement like NOT X, the assembler itself cannot deduce how big this piece of memory is, so I need to specify a size. So for example, maybe I know X is a byte. So that's how we can use the NOT operand. What's the next in our toolhouse? Well, we know from discrete structures and general programming, we have AND, OR, and XOR. So we're going to go through that sequence and then try and do more complicated things with them. So here's our little refresher table, where obviously if I AND 0 and 0, I end up with 0. If I AND 1 with 1, I end up with 1. And if both are not true, it's going to be false. So the biggest thing I want you to take away from how to use the AND operator, apart from what the semantics of the instruction look like, is its intent. Now, you can think of a bitwise AND as simply ANDing together 2 bit strings, but the common way it's interpreted is that AND is a bit selector. So what do I mean by a bit selector? So let's look at these examples over here. Now, think of the left operand as the bit string you wish to manipulate, and you want the result of said manipulation to be returned. So what's happening with the right operand is I'm specifying which bits I want to select. So if I have a 1 over here, it means I want to select the corresponding bit in my original string. So if I have a 1 over here, it means I want to carry over whatever bit was over here in my original string. The same thing for all places where I have a 1. So what you'll see at the end here is I've selected these bottom 4 bits because I had a 1 in each of their locations on the right-hand entry. So I selected these 4 bits from this left-hand string. Now obviously, I mean, you can swap the meaning and have the right-hand side be the one that you're selecting from, and the left-hand side one to be a selector, whatever's easier for you. But this notion of thinking about it as a bit selector is very powerful. The next example here is pretty much the same idea. The difference is you see I'm selecting the top 4 bits, and that's what I end up selecting from my original string on the left-hand side. You'll often see people perform these operations directly on hex values. So here, my original string on the left, and what's happening in here is I say I want to select FF, And remember, each F corresponds to 4 ones. So in essence, what I'm saying is I want to select the bottom 8 bits, or in this case, the bottom 2 hex values. So I simply extract AB. And the higher order bits in this case would all be zeros because I didn't select any of them. I just selected those lower order bits. You can see this even in a more complicated example where, say, I've got this long full 64-bit hex example, and I AND it against this long string. Where I have zeros, I'm basically not selecting. If I have an F, they're all ones, and I'm fully selecting those hex values. So you'll see didn't select, did select, didn't select, did select, and so on. Now, obviously, if I have something like a D instead of an F, I'm not going to fully extract the whole hex value because D will map to a different binary string than just all ones. So try and go through this example again, and instead of having F's in all these locations, have D's and see what you end up getting. So how do we use the AND instruction in assembler? Well, unlike NOT, it has 2 operands, a destination and a source, where the right-hand operand is going to be your source and your left-hand operand is your destination as normal. And your source can be either an immediate value, so a constant or a memory location, or it can actually be a register. The destination itself can either be a register or a memory, but as with our previous instructions that had 2 operands, both the destination and the source cannot be in memory. Okay, so I cannot have an AND with 2 things that are actually in memory. One of them at least has to be in a register. Unlike NOT, the AND instruction does set flags. So it sets the sign flag and the 0 flag. And those we can use when we get to more complicated jump statement. But it's good to keep in mind that the result of the AND, so whatever is stored in that destination register, will trigger what the sign flag and the 0 flag should be. So let's look at 2 examples of using AND. So this first one, what we want to achieve is we want to extract bits 0 through 3. So it's basically the bottom 4 bits of a given value and store them in RBX. Okay, so I just want to extract that bottom nibble. So here in this example, the bit string I want to extract from is 1, 2, 3, 4, 5, 6, 7, 8 in hex. So I'm going to make a copy of that into RAX, so it's ready to go for the calculations. The next thing I'm going to do is I'm going to make a copy of RAX and move it into RBX. Now the reason I'm doing that in this example is not entirely necessary, but the reason I want to do it is that if I'm about to perform an AND operation to extract from that bit string, I will destroy it in the process. So I want to make sure I have a backup. So I'm going to basically perform the AND operation on my backup and leave RAX to contain the whole value. So RBX has the string as well, and I just want to extract the bottom 4 bits, which would correspond to this hex value 8. So all I have to do is go AND RBX and use the hex value F. I could have, for example, also used the binary 111 if I was just indicating it's a binary number, which you can do as well as the immediate one. And what will be left in RBX is simply 8. Okay, so very straightforward to do it. What becomes a little bit more difficult with the tools we have available at our disposal currently is, say I want to extract the second nibble, so bits 4 to 7, and store them in RAX. How would I actually go about doing that? So for this code segment, assume that RAX still contains this bit string over here. Now, how would I actually go about extracting just those bits and store them in RAX? So in essence, for this example, I want to store the value 7 into RAX. How would I achieve it? Now, there's a trick that's quite useful, is that if I have a binary string, if I divide it by 2, I shift it right by 1. Now, you can see this naturally that, for example, if I have 16, this is just a simple example, but say I have 16 as binary, and I were to divide it by 2. So I wanted to say, what's the division of this? So, well, the division of this by 2 is simply 8, which would correspond to 1 followed by 3 zeros, which is actually just this string shifted right by 1. And when it gets shifted right by 1, this falls off the side. So I'm just left with the value that I'm looking for. So that means if I wanted to get bits 4 through 7 to actually be in location 0 through 3, I would need to shift right 4 times. Now we don't have a shift operator yet, we're going to get to one, but at the moment we don't have it available. So how could we achieve that? Well, I just said if I divide by 2, I shift right once. So in essence, I just need to divide by 2 4 times, or equivalently, I can just divide by 16 once. So let's use our division that we learned from the previous lecture. So RAX still contains our binary string, and I want to now try and perform a divide. So recall that when I perform a division in assembler, I actually am dividing RDX followed by RAX divided by whatever I specify. So it's actually both those bits combined. So I just need to zero out the RDX so it doesn't somehow interfere with my answer. Then I'm going to move 16 into RCX just so it's ready to go when I perform my division. I'm then going to call IDiv, which will divide RAX by 16 and store the result in the 2 corresponding registers. So in this case, the bit that we're interested in is going to actually be the quotient, and all we want to do is extract the bottom 4 bits again, so we simply AND it with F. And what will be left in RAX at this point is going to simply be 7. Now, if this was a little bit unclear, what I highly advise you do is to replicate this kind of example, and at each step of this code, I want you to analyze what is in all of the registers using GDB, just to kind of make sure that your intuition matches with what you're finding. So moving on to the next instruction, we have the OR operation. So again, a little revision lookup table. Obviously with the OR, if either one of the operands is in fact true, or in this case 1, the result will be 1. And we have our logical version as well as our bitwise version. Now the important thing for us, and from an intuitive perspective, what you should try and gain, is that an OR operation can be used as a bit setter. Okay, so an AND was a bit selector, whereas an OR is a bit setter. And the way in which you interpret this is very similar to what we did in the context of the AND. So you think of your left operand as being the bit string you wish to manipulate. And the second one, or the right-hand operand, is the way in which you would want to manipulate that string. So in this case, I want to set the first bit, the second bit, the third bit, and the fourth bit. So regardless of what they were originally, in my output string, I want those bits specifically to be 1. If I have a 0 present over here, it simply means that whatever was in my original string should be preserved. Okay, so I don't set or reset it, I just let it pass through as such. So for this example, again, all that's happening in reality is I'm doing a OR at a bit level, but I feel this notation of a bit setting is useful. So I actually want to set the bottom 4 bits to be 1, and you see in my output string I have them all as 1, and then the rest of the bits, this top nibble, is simply carried over. So you see that gets carried over without any kind of change. Again, we can try and look at the other way around. Say I want to do a bit set on the top 4 bits. I'm just going to get them all set to 1, and the lower order 4 bits will simply be carried over as they were. Again, we can do the same thing using hex. There's nothing particularly different there. You'll see that all I'm saying now is that I want to carry this binary string over. In this case, it's the hex string, but I want to OR it against FF, which means I want to make sure my bottom 8 bits are all set to 1. So in my output, I will have this FF, and everything else from my original string simply gets carried over. Okay, same thing applies with a slightly larger example where I'm specifying that I want these specific pairs of hex values, or bits, or bytes rather, to be set to F in the corresponding output string, and everything else should just be carried over unaffected. The OR operation, again, exactly like AND, has 2 operands, a source and a destination. The source can be an immediate value, a memory location, or a register. The destination, however, can only be a register or memory. Both the destination and source cannot be in memory. And lastly, similar to the AND instruction, the sign flag and the 0 flag are set once you use the instruction. So here's two quick examples. Of how we can use OR in a practical context. One of the nice tricks with OR is that I can set a number to be even by simply ORing that number with 1. And the reason that works is, all binary numbers, or all numbers, obviously have a binary corresponding representation. So say I have this number over here. If I OR this, with 1, what I end up getting is the bottom bit will be 1 and everything else will be as it was before. But the only way for a binary number to actually be odd is for it to actually contain a 1, because all of these other, 1 in the lower order bit, because all of these other components correspond to powers of 2, where it's 2 to the 1 all the way up. This is the only place where I can get an odd number induced into the sum. So if I set the lower order bit of a binary string to be 1, the resulting number is going to be odd. So it's a very quick way of actually checking or setting a number to be odd. And actually in a similar vein, it's a very quick way of checking if a number is odd is by simply checking its lower order bit. Here's another example where I want to do a bit of bit setting. So I want to take this hex value and I want to set the top two hex values to simply be Fs, so they must all be on. Again, all I do is I move my immediate value into RAX, and then I simply OR RAX with the bit string. So again, all that's happening here is I'm setting the top two bits to actually be F. So the output in this case is actually simply going to be FF00, at least what's left in RAX. If, for example, this original one over here was, say, 0x10, let's say AA, and I perform this operation, what I would end up getting out is going to be FFAA. Okay, now just a little bit of homework for you to ponder, and I want you to try and figure out how I would actually be able to make a number even. Okay, how, if I was given an arbitrary number, how would I ensure it was even? Moving on to another operation that I'm sure you encountered when you did discrete structures, but probably one you don't use as frequently when you've been coding, is the exclusive OR operation. Now, the way in which we perform an exclusive OR is by using this kind of upper arrow, which you often see for the use of power. And it's actually a reason that people often make mistakes with C++, because they might write something like this, hoping that it's an exponent, and actually what's going to happen is it's going to do an exclusive OR between the binary for 7 and the binary for 2. Now, just as a recap on how exclusive OR works, basically if I have two inputs, the answer will be 1 only in the situation where the inputs are different. So here we have 0 and 0, so we get a 0. Here we have a 1 and a 1, so we get a 0. Here we have a 0 and a 1 because they're different, we get a 1. Here we have a 1 and a 0, and because they're different, we get a 1. Okay, so exclusive OR, the two inputs have to be different. Just like we had in the case of AND and OR, there are useful kind of practical ways of understanding what these instructions do other than just working at a pure bit level, kind of a high level feel of what they're trying to achieve. Exclusive OR can be seen as a bit flipper. Okay, so again, if I look at this left-hand string as the string I wish to manipulate, and the one on the right dictating how I'm going to manipulate the string, all that this indicates is that if I have a 1 here, I want to carry over this whole string from the left-hand side, but I want to flip what was ever in this lower order bit. So you'll see I get the original string as it was before, all the way up until the bit that I decided to flip, and in this case it will be a 0. That's because I had a 1 there originally. So all the exclusive OR does is it will dictate which bits I should flip. So in this case here, if I exclusive OR a random binary string with all 1s, I actually perform a NOT operation in that I will set everything to be the opposite of what it was. So it will be a 1, 0, 1, 0, 1, 0, whereas originally it was a 0, 1, and so forth. Now I should make it clear that this is a NOT operator on a limited space. I mean, this will only NOT as far as you've specified, whereas NOT does the entire register, obviously. This will only NOT for how many bits you actually list in the right-hand operand. You can apply this to many contexts. I can obviously do it directly in hex values. I want you to actually, as an exercise at home, I want you to try and figure out why if I XOR AND and F, I end up with the value of 5. Seems a bit counterintuitive, but if you just consider the fact that this is all ones, and A has a corresponding binary meaning, and I were to simply flip all the bits in an A, what would be left and what would its corresponding hex value be? And then you'll end up getting to this straight away. This last example is something that's quite interesting. And it's the idea that if I XOR a value with itself, I actually set it to 0. I mean, this makes perfect sense. If I have a random binary string, say 1101, and I XOR it with 1101, what I'm basically saying here is that if it was a 1, make it a 0. If it was a 0, do nothing. So by XORing against myself, I end up setting the value to be 0. And you would have actually already seen that in some of the examples from the earlier slides, where we try and store a value in RAX as the return value for the main function, and we do so by sometimes XORing out the register. So how do we use XOR? Very much the same as AND and OR. 2 operands, destination and source, same conditions as before, same flags set as before. But there's something that I want to kind of bring to your attention, which the book does mention, but only quite a bit later on, is why do we actually use XORing to set a value to 0? It feels a little bit of like a superfluous trick that may not be necessary. And I mean, in principle, if I wanted to set RAX to 0, this first version is perfectly acceptable, okay? Unless I'm asking for efficiency, works perfectly fine. It's also by far the clearest. If, however, I were to say XOR RAX with RAX, that will still result in RAX being 0, but the instruction actually takes up less space. So if you look at your listing files, you'll see that if I have this move with a 64-bit register in it, that instruction takes up 7 bytes. But an XOR instruction with a 64-bit register only takes up 3 bytes. So it saves you 4 bytes each time you use an instruction like this. Now, by and large, it's really a kind of minuscule saving. I mean, if you're writing a big program, I wouldn't worry too much about optimizing for something so small. But in earlier computer systems, 4 bytes being free is 4 bytes. And actually, even on modern systems, if you have a very, very small piece of embedded software and you want to constrain how much memory the system needs, because then it makes manufacturing of that machine much cheaper, you might try and actually use operands that do the same thing but simply take up less space. There's nothing lost by using the second approach. There's only something to be gained. That's it. I suppose the place that you can lose is in the context of clarity. If you're not used to this trick, it's going to seem less clear than simply setting it to 0. This brings us to the third one, which is kind of a more subtle one because it relies on 2 tricks. The first trick that we were using is this idea that if I XOR RAX with itself, it's 0. So that's trick number 1. But the second trick that this last one uses is that if I have my answer stored in a 32-bit register like this, just like we had with addition and moves, I 0 extend. So what actually happens here is I XOR the bottom 32 bits with itself. So let's say this was my 64-bit register. I end up XORing these two with each other, and the result will end up being 0 in all of those 32 bits. But because I did an operation with the resulting size register being 32, so it was a 32-bit register, I 0 extend, so I end up getting zeros all the way up to the top of the register as well. So it kind of achieves, well, it achieves exactly the same thing as the first two, but it relies on these 2 tricks. But the reason we would do it, even though it's maybe less clear, is that it actually saves us an extra byte, because an XOR operand on 2 32-bit registers only takes up 2 bytes to store, whereas the XOR operation on 2 64-bit ones required 3 bytes to store. So let's look at a couple of practical examples of using XOR. So here's exactly what we are discussing. The first one's straightforward. I want to XOR out RAX. So instead of setting or moving 0 into RAX, I can XOR EAX with itself. It will set the bottom 32 bits to 0 and 0 extend the top 32. So RAX will end up being 0. And obviously, if I want to perform a bit flip on a part of a value, I can as well. So say I've moved the hex number 1234 into RAX, and I call XOR, and I'm going to XOR that hex string against F. This F is obviously going to correspond to 1111, which tells me I'm going to flip all of the bits that are actually in 4. And what will end up happening is I'll end up getting a B. That's because 4 obviously is going to be 100. I now flip all of the bits because I'm XORing it against 1111. I end up with 1011, and this corresponds to obviously 8 plus 2 plus 1, which is 11, which in hex is simply B. This last one is an interesting trick. You don't see it as often anymore, but it's a way of swapping two variables without having to use a temporary value. So normally if I had two variables A and B and I wanted to swap them, I would need to use a temporary variable, or at least that's the default way in which you've been taught to do that swap. But this is a way of doing a swap between two values without needing a third variable, or in this case a third register. So what this code achieves is it's going to put whatever was in A in whatever was in RAX into RBX, and whatever was in RBX into RAX. So I just swapped the values of RAX and RBX, but without using a third register. Now you might wonder, how on earth does applying XOR 3 times swap the two values? Now, you can play with some examples to get an intuition of why it works, but we can actually quite easily prove it to work. So instead of writing RAX and RBX the whole time, let me simply use A for RAX and B for RBX. So I start with A and B, and I want to try and swap them. So what are these instructions doing? So the first instruction is basically setting A to be equal to A XOR B. By the way, that's the notation for XOR, just common notation for it. Then I'm setting B equal to B XOR A. Then the last instruction is I'm setting A to be A XOR B. Okay, now I want to actually try and show that this will actually do the swap. So let's start with this first one over here. So start with this B to see what will be stored in B, because you see I don't change B against after this instruction. So it's a good place to check that things are working as I expect. So I'm going to write out, put a 1 there, let's write this out in a bit more detail. So B is equal to B XOR A, but you see that A got replaced in this line over here. So this is actually B XOR A XOR B. Now, luckily for us, we have commutativity, so I can rearrange how this actually works. So what ends up happening here is I actually have B XOR B XORed against A. Now, B XOR B is simply going to be 0, and 0 XORed against A is simply going to be A. Because obviously if I have 0, and we consider the fact that XORs do bit flips, it means we don't want to flip any of the bits. So if I XOR A with 0, I end up getting A. So great, now B is actually A as wanted. So now we just need to confirm this part 2. So let's try and do that. Let me just write on the top here. So we have that A is equal to A XOR B. Now, obviously, B and A have changed. We already showed that B is in fact just A, but the A is actually this A over here. So we end up actually having A XOR B XOR A. So that came from this calculation 1, and then this bit came from the first step, so it came from star. So same trick as before, we simply rearrange, we end up getting A XOR A, XOR B, and again, it's just 0 XOR B, which is just B. So now A is equal to B and B is equal to A, and we performed a swap. So that's why that works. You don't see that proof often. I don't think it's in the textbook, though it's very straightforward to actually verify that it does work. If you're actually interested in programming competitions, you'll find this kind of trick using a lot of XOR or bitwise operations to achieve interesting properties is quite prevalent. Cool. Now we can go to an operand that we're kind of hoping that we would have gotten to earlier in some ways, because we already did a shift. We just did a shift the hard way. But luckily there's a way of performing shift in assembler and C++ without having to resort to performing divisions. So how do we go about it? Well, we have two shifts at our disposal. We have a left shift and a right shift. And the way in which they work depends on actually whether or not the number is signed or unsigned. In assembler, we actually explicitly make the distinction of what type of shift we're performing. In C++, it's inferred by the data type we're working on. So left shift is the same regardless of whether or not we have a signed or an unsigned number, and all that ends up happening in the case of a left shift is that, say I have the binary string, say 1 0 1 1, and say these are all zeros right up until the top, and I perform a left shift. All that happens is that if I shift it to the left by 1, I induce a 0 on the right and I remove the higher order bit. So you can think of me moving the string to the left and I have this magic 0 that pops into the string. But as a result, I lose the higher order bit. So for everything I gain, I lose on the other side when I perform a shift. Now again, this left shift is actually the same as multiplying a number by 2. Just as the right shift that we ended up using previously actually was dividing a number by 2. Left shift is the same as multiplying the number by 2. In terms of right shift, if I have, let's start with the unsigned version. So if I right shift a number in C++ and it's unsigned, all that happens is I induce zeros in higher order bits. So again, say I have the same example and I right shift, all that will happen is that at my higher order bit, I'll add a 0. So this was my new bit that I just added. So ignore this for the moment. So I just added a new 0 and this bottom bit fell off. Okay, so that got shifted off the right hand side and I induced or added this extra 0. If, however, I'm performing a right shift on a signed number, things are a little bit different. If the number is positive, it will happen exactly as I described here, where we shift the bit string to the right and obviously everything that is no longer within frame falls off the right hand side. So if I shift by 1, we lose 1 bit to the right, but I always add a 0 to the higher order bit. If, however, the number is negative, instead of adding a 0 to the higher order bit, I add a 1. Now the reason I add a 1 is that because the number is negative and it's in this 2's complement notation, I will always have a 1 as my leading bit, my highest order bit. So if I shift by 1 to the right, again it's the same as dividing by 2, but if I have minus 7 and let's make it an easy number, say I have minus 8 and I want to divide by 2, then I end up with minus 4, but it means I still need to have a 1 in the higher order bit. I can't have a 0 because that would mean that in 2's complement notation, by dividing by 2, I ended up making my number a different sign. I converted from negative to positive, which isn't obviously what happens in practice. So this is what's referred to as sign propagation, in that whatever the sign bit was, whatever the higher order bit was, is the bit type that is introduced when I perform the shift. So if I shifted right by 5 and the higher order bit was 1, I will actually insert 5 1s as the higher order bits. And obviously 5 bits will fall off on the right hand side as a result of the shift. But the big difference is if I have a signed number, we propagate the sign. And if we don't have a signed number, we just always introduce zeros. There's no distinctions. Okay. So here we can see some examples. So the bottom one is just a nice one where I'm going to shift right by 3. Now in this case, you can assume that there were some leading zeros for this example. So I shift right by 3, and what ends up happening is that this guy falls off the cliff, falls off the cliff, falls off the cliff, and we're just left with these 3 bits. In a similar vein, if I shift left, what happens is all of these guys shuffle to the left. Now, in this case, I have enough space so no one falls off the other side of the cliff, because we've got a bunch of zeros before we hit the capacity. So say this was a 32-bit number for argument's sake. But what happens is as I shift to the left, I introduce a 0 for each shift that I made. So in this case, I shifted left twice, and I introduce 2 zeros in my lower order bit. You can actually see here directly this example where I perform a shift. So if I shift, or a shift to perform some kind of multiplication, if I shift left 125 by 2, so again, this is in C++, I'm doing the shifting. If I shift left by 2, I end up multiplying it by 2 and then multiplying it by 2 again. Because remember, each shift is one multiplication by 2. So it's the same as multiplying this number by 4, which gives me the value of 500. And if you look at a binary level, you can see this very clearly. I mean, if I converted 125 to binary, I'd get the following binary string. If I shifted left by 2, I introduce 2 more zeros, and if I convert back, I get 500. Now this makes perfect sense, because if I look at that 1 there, before the shift it represented 2 to the 0. After the shift, that 1 that was over there now represents 2 to the 2. And you can see here this is the multiplication of 2, and the same thing applies to all of the bits, which is why we get this behavior. You can obviously also perform the same kind of idea directly on hex numbers. So for example, here I'm going to shift right the following, assume this is going to be in this case it's a sign or unsigned shift. I'm going to shift right, and then what's going to happen is I lose 4 bits on the right hand side. So just like there we lost 3 bits, in this case I'm going to lose 4 bits. But our 4 bits are all stored in that one hex value D. So then I'm going to end up getting A, B, C, D, and ABC, and that D will have fallen off the cliff based on the shift. Now, when you work with hex values, you should maybe be cautious, because if you don't shift by multiples of 4, and say I shift by 3, I'm going to actually get completely different hex values there. And it's just because of the fact that now all of the binary numbers are a little bit offlined with how we actually construct our hex values. So as a little example at home, I want you to actually try and look at 0x, A, B, C, D, and I want you to shift it right by 3 and try and figure out what the string will actually be. And you can obviously do it in assembly if you want to confirm your calculations, but I want you to try and do it directly in the context of this example and see what's happening. Test it, make sure you understand how everything works. So how do we do these shifts in assembler? Well, I mentioned in the C++ context, it's kind of implicitly determined based on the type that we're working with, what type of shift we perform when we do a right shift. In a context of assembly, you have to make it explicit yourself. You have to know what type of data you plan on working on. And the way in which we distinguish between a shift that propagates the sign bit and one that doesn't is a shift that propagates the sign bit is referred to as an arithmetic shift, and one that doesn't is simply called a shift. So we have these 2 types of shifts. We have a shift left and a shift right, and the mnemonics are quite easy to remember, SHL and SHR. We then have shift arithmetic left and shift arithmetic right. Now, something that can cause confusion is shift left and shift arithmetic left are the same operation, because we don't affect the sign bit by shifting left. We might change it by shifting something in that is of a different sign, but that's not where we're adding bits. We're adding bits on the right hand side, so we can't propagate a sign in that context. Just as a general note, that if you do perform a left shift on a negative number, it is possible that you end up getting some odd behavior if you pushed off that leading one. But that's more of a C++ issue than will be relevant to us, but it's just something worth noting. Now, the big thing is if I want to do a right shift and my number is signed, I need to use the arithmetic shift, and if my number is unsigned, I'm perfectly fine using simply the normal shift, okay? Now, I wouldn't recommend that you always use arithmetic right shift. I've seen in some situations that there's a misunderstanding that a student might think, well, if I always just propagate what the sign bit is, isn't that always fine? It's not in the context that higher order bit might be a 1, but it's in an unsigned context. So when you shift right, you want the number to become smaller. But if I'm propagating the sign bit, then it actually won't necessarily happen because I've now introduced a leading 1. So I'm not going to get the behavior I expect. So you definitely need to figure out which shift to use based on whether you have an unsigned number or a signed number. Okay. Now all of these shifts have two operands. The first is the destination, and it's either a register or memory. And the right-hand operand is an immediate value. So you might say I'm going to shift left by 3, and you can specify that as immediate value. It is possible to actually use an 8-bit register as the right-hand operand. It's from old assembler, but by and large I recommend you simply use immediate values for the shifts unless something else is a bit fancy, in which case you can use an 8-bit register, and only the 8-bit register works there. But for most examples, just use the immediate value, it will be fine. Once again, as in normal context, if I want to perform a shift, so say I have shift left, and instead of saying RAX4, in this context the sizes are all clear. If I'm in a situation where I want to perform a shift on memory, I want to have something like X, I'm going to need to specify the size if I work directly on memory. So that doesn't change in this context. Now, we do actually set some flags when we perform shifts. So we set the sign and the 0 flag. Okay, this is obviously good to know to check that maybe I didn't get some weird overflow issue, because if I have a unsigned number, if I have a signed number and it's very large, and I perform a left shift and I change the sign bit now to be a 1, which can happen, it's maybe worth me checking that happened. So in essence, it's a variant in overflow where I doubled my number and it became negative, which is obviously not ideal, so I might want to check for that. The other thing is the carry flag is also set, and it's set to the last bit that was shifted out. So you can actually do the direct checks from the textbook when we're discussing whether or not you have overflow or not, because you can check the sign bit and you can check what carried out. So in essence, you know what carry out and carry in is in this case, from which you can actually determine exactly what occurred. So it's definitely something to not forget. Now let's look at two more practical kind of combination approaches to use multiple of the bitwise operations we've discussed. So earlier on we had a simple example where we extracted some lower order bits, and then we try to extract some higher order bits, but we had to do a little bit of trickery in that we had to divide. Now that's not the most scalable approach, it's also quite inefficient. So we're going to try and use some of our newer operations we've discussed to extract a bit field. And by extract a bit field, I simply mean that if I have this long bit sequence, let's say it's 32 bits or something, and I actually want to extract just these 3 bits out, how do I go about doing that? Now, with a lot of these bitwise techniques of extracting and filling that we'll discuss, there are a couple of ways of doing things, but I'm going to show you what I feel are the most direct ways of actually achieving this. So the first thing is, say I want to extract a contiguous chunk of memory. This technique that I'm going to go through is for a contiguous chunk of the bit string, and I want to extract bits k to m inclusive. Okay, so basically we would say that's, for example, bit k to bit m. In this case, m is greater or equal to k. And how do we go about doing it? So the first thing that we're going to do is we're going to shift right k bits. And once we've shifted right k bits, what that would end up doing is it will end up putting this k at the lowest order bit. Then we're going to AND, so this is where we're using the bitwise operation, we're going to AND this value with a mask of m minus k plus 1 bits, okay, where this mask has all entries set to 1. And that will actually have extracted the field that we want. You'll see when I start going through more complicated little algorithms for doing these kind of extractions, it may be a little bit hard to follow the steps as such, but as soon as you see it in an example form, it will make a lot more sense. Now, just as a minor note here, you'll see this trick used quite frequently. It's not really a trick, it's just basic math, but the size of that contiguous chunk from k to m is simply m minus k plus 1. That's how many bits are inside this contiguous chunk we wish to extract. Okay, but you'll see that calculation pop up again and again, so it's worth me just reiterating what it is. So let's look at this approach via an example. So let's say I have a 16-bit register, just so it can fit nicely on the screen. I've just annotated the indices at the bottom just to make discussing things a little bit easier. And I want to extract bits 3 to 9, okay? So how do I go about doing it? Well, we already have a procedure, but we can look at the procedure more directly and we'll see how to do it. So the first thing I want to do, just note this sequence of operations would destroy the register in the process of extracting out the bits. So if you didn't want to destroy what was stored there, you'd need to move the data to a new register and then perform this procedure on that register. The first step we discussed is we need to shift right by k bits. So in this case, k is 3. So basically, we make sure that this bit is right at the bottom, and as you'll see, everything is just shifted right. Now in this case, we obviously, by shifting right, we've incurred some new zeros, but it's not relevant for our purposes. We'll see it will vanish shortly. And then we need to perform the next step, which is to AND this against a mask of m minus k plus 1 in size. Okay, so in this situation, m minus k is just 9 minus 3 plus 1, so it will be 7. So I need to make a mask of 7 ones, which actually just corresponds to 7f in hex. I'm just filling up the zeros just to make things very clear. Then I'm going to perform my AND operation across these two, and what I end up at the end will just be the bit sequence that I wanted to extract. Now remember, AND is a bit selector. So by having a mask like this, I'm in essence saying I want to select all of these bits. So in this case, I want to select these 7 bits at the bottom. Once I've done the AND, I have the bit field that I wish to extract ready to go in whatever register I was performing these operations on. Now the upside is I didn't have to perform any divisions or anything to achieve this. Now, for this example, I recommend maybe try and write this for yourself in Yasm just to make sure you can recreate it, but it's very straightforward from what we've discussed, but just make sure you can always implement these algorithms yourself directly in assembler. Now, there's another way, which in some ways is perhaps more intuitive, depending on how you kind of envision these problems. The downside is it kind of relies on the size of the register that you're actually working on, whereas the other approach didn't really cater for the size of the register so much, but you'll see what I mean shortly. So an alternative way of extracting our bit field is that we're going to use a combination of shifts, okay? But we're going to do so in a way that kind of exploits the functionality of the shift more directly than before. So the idea is that we're going to start by shifting left until bit m is the highest order bit. So basically, I would shift such that this one is all the way at the top, okay? Then, to achieve this, I would need to shift left by 63 minus m bits. Now this works in the case of a 32-bit register. If it was in the case of a 64-bit register, if this was a 32-bit register, then I would simply use 31 over here instead of the 63. So I'm going to do the shift left of 63 minus m bits. Then I'm going to shift all the way back right. So I started with this left shift, and then I'm going to shift very far back to basically undo my previous left shift. And then I'm going to go an extra k bits further to the right. Okay, so this expression there is just the same as going 63 minus m plus k. So basically I'm undoing my old shift. So I'm undoing the left shift that I did before because I'm now shifting right, and then I'm going to shift a further k bytes. Now, what's in essence happening here is when I shift to the left, I'm basically destroying those higher order bits that I'm not interested in. When I shift back right, I'm only going to do, in this case, a non-arithmetic shift, which means I'm going to do a normal shift and I'm going to incur just zeros on the left side as I shift right. And then all the lower order bits that I wasn't interested in are going to also fall off the right-hand side once I've done that right shift. So let's see this in the example. So again, we want to extract 6 minus 3. We want to extract bits 3 to 9. So it's just this 7 contiguous bits. First step is I'm going to shift such that this higher order bit at 9 is moved to the top. So in essence, what's happening is by doing this operation, all of these bits get kind of shifted off the cliff, and they've destroyed once we've done the shift. They're not preserved in any way using a normal shift. They're just basically wiped. And you'll see now that we actually, in this process, we incurred a bunch of zeros, but again, it's not really too much of a concern. Then we're going to shift right, in this case by 9 bits, but basically this, and you can get this 9 from that formula, but basically it's a shift such that this lower order bit ends up all the way at the far right. If you want to think of this in a slightly easier fashion, you can think of it being a left shift followed by 2 right shifts, where I do the left shift, then I undo it such that my bits are basically in this position again. Just the higher order bits will all be 0. And then I perform my final right shift to kind of get this field to the bottom where I want it, so I can actually deal with the actual bit field that I wanted. You don't have to do it in 2 steps. This is obviously the most efficient way, that I do a left shift and then a right shift, and then straight away I get my bit string. Now I personally feel like this is an easier approach, or at least intuitively easier than the other one, but each to their own in which way you find more intuitive. There's often a couple of ways of solving these type of problems. Now there's one more instruction about general bitwise operations that I want to introduce. It's not one that you can really access in C, but you can in assembler. Well, you can't directly access it in C, I should rather say. In assembler, we have access to what's called a rotate instruction. Now we can do a right rotate or a left rotate. So for right rotate, it's ROR for rotate right, and ROL for rotate left. And it operates very similarly to the shift. The difference is that instead of those bits falling off, they wrap around. So if I were to, for example, say I had a very small little bit string. So let's say it's only 4 bits. Obviously, all our bit strings are going to be longer than this because we work with 16-bit, 32, and 64. But let's say we only had 4 bits. Normally what would happen is if, say, I had this string over here, and I was to perform a right shift of 1, I would end up in a situation where I'd get 0, 0, 0, 1. Okay? So what would end up happening is that this bit would fall off, and I just increase or add the 0 at the top. However, if I'm in the context of performing a rotate as opposed to a shift, so if I were to rotate right by 1, what I would actually rather end up getting is that this lower order 1 would get moved to the top, and then everything would shift. So I'd end up getting 1, 0, 0, 1. Okay, so the trick here is that I don't lose that lower order, but it rotates around to the top. So it becomes a cyclical approach. So if I were to keep rotating, I would eventually end up getting my bit string back to its original size. Now the place where the higher order or the lower order bit goes will always be the highest order bit, and that will depend on how big your register is. So for example, if I'm performing a rotate in a 64-bit number, that lower order bit would go to the 64th bit or the 63rd indexed bit, and the same thing would apply for smaller registers. Okay, so it gives us a way of performing a shift-like operation, but without destroying the data, which in some situations is useful. Now, in the last example, destroying some of those bits were useful because we wanted to clear it out. But we'll see now in one of these examples that just using the rotate means we can actually get some nice functionality quite easy and rely on the fact that we don't accidentally lose data in the process of shifting. Now, how do the rotate operations work? Very much in line with how shift works. We have 2 operands, and the first is both the source and the destination. So it's the register or memory location you wish to perform the rotation on, and it's where the result is stored. The second operand is the number of bits you wish to rotate, and normally that's going to be an immediate value, but you can use a register like CL. Okay, so you do have the ability to use the old 8-bit register if necessary. So let's look at this little example just so we can see it in practice, other than the one I used at the top. So let's assume we're working on 16 bits here. Okay, so you can think of this would be in the context of, say, like an AX register would be 16 bits. So here, obviously these aren't assembly instructions. This is just to demonstrate the behavior you would get. Say I have 1 and I want to right rotate it by 2 positions. So this on the left would be the long bit string, so I just haven't included the zeros. And what would happen is that when I rotate 1, this 1 would go to the higher order bit, and then when I do the second one, it moves 1 up. So in essence, it went from being here to the second highest bit. So I've rotated this whole sequence by 2 to the right, and as a result, I've moved what was the lowest order bit to the second highest bit, and what was the second lowest bit to now be the highest order bit. Now you can also perform rotations like this directly on hexadecimal values. So if I, for example, perform a rotation of size 4, it means that I'm moving, say, D will get moved to the top. Again, this is all assuming 16 bits, but if I were to rotate right by 4, I end up getting D, A, B, C. Now note again, if I have A, B, C, D, and I rotate it right by 3 bits, what do I get? Now again, because it's not a multiple of 4 and I'm working with hex numbers, I'm going to get a result that doesn't resemble this at all really, because all of the things are misaligned. But again, nice example to check your understanding on. I can also obviously rotate left. If I rotate left, what ends up happening is the higher order bit moves to the lower order bit. So in this case, what ends up happening is, if by rotating left by 4, is that these 4 bits that make up this hexadecimal value move to the front. So then I end up with 3, 2, 1, 4. Okay, and if I were to, for example, rotate this value by 4 to the left again, then I would end up getting 2, 1, 4, 3. And obviously, if you keep proceeding, you'll eventually get back to the same string you had before. So let's try and actually do a slightly more complicated sequence of operations. So the aim here is I want to fill a field in my bit string. So by that I mean that I have my long binary string again. And I've decided that I actually want to insert some predefined string at this location. So say I want to insert 101 at this specific part of the binary string. So I've got some field I want to insert into my binary string at a specific location. Again, all contiguous. How do I actually go about doing that? So I want everything else to stay the same. So basically, say this example was just making up a small little example. So say that was the original string. After this operation, I would want to be in a situation where everything stayed the same except the bits where I'm inserting. So now this would correspond to this. So we would end up having 1, 0, 1, 0. Okay, so in essence, I filled this field with this predefined value or some value that I got from somewhere else in my code. Now, how do I actually go about doing this? Now, there are, again, a couple of ways. I'm going to show you 2 ways of doing it. I think the textbook has one of these 2 ways, not both. But nonetheless, again, there's many ways of doing these kind of operations. So the first thing is I'm going to go through these steps of the algorithm. And at first glance, they may feel a bit unintuitive. But again, as soon as we see the example, things will become much clearer. So first, just to be clear, we have kind of an original bit string, and we have the field we wish to insert into that bit string at a specific location. So let's say we're working with a 64-bit register and we plan on filling bits k to m. Okay, so we want to insert our predefined or our stored bit field into the bits k to m in our current bit string. So what we first do is we prepare a mask of size m minus k plus 1 bits, where all of the bits are equal to 1. So basically we want a mask of 1s that is in length equal to the size of the contiguous chunk we wish to fill. Then we're going to shift the new value in the mask left k bits. Then we're going to negate the mask. Then we're going to AND the old value and the mask together. And then lastly, we're going to OR the new value that we got from this operation. So we're going to OR in the new value for the field using what we got for the previous calculation. Now that feels like a bit of a mouthful, but you'll see exactly what's happening as we go through the examples. I think the example is almost more useful than this procedure, but this is obviously useful if you want to actually code it up yourself. So here, again, I've just annotated a 16-bit example so we can fit it onto our screen nicely. And I've indexed from 0 to 15 just to make the discussion easier. So what I want to do for this example is I want to replace bits 3 through 6. So in this case, it's the ones that are indicated with this kind of reddish-orange color. And I want to insert this bit string in that location. Okay, so how do I go about doing that? Well, we're going to follow our algorithm that we discussed before, but we'll see why it works as we proceed. So the first thing I'm going to do is I'm going to make that mask. So that mask is going to be 0 everywhere, but then I'm going to have 1s equal to the size of the field that I'm trying to insert. So in this case, we have 4 bits, so I need to have a mask of 4 contiguous 1s. Then the next step is I'm going to shift both the value that I want to insert, so this was the value I wanted to insert, so I'm just going to say V, and my mask left by K. Okay, now the reason I'm shifting it left by K is to ensure that this mask lines up with the location in my original bit string. Okay, we'll see why I want it lined up shortly, but that's why I'm shifting it by K. So I shift left by K bits. Then I'm going to negate my mask. So basically I'm going to have 1 everywhere except for the location where I previously had the 1s. And now this is where the trick of this approach comes in. I'm going to AND this mask with the original string. And what will end up happening here is that I will end up with my original binary string, but in the bit locations where I want to insert my new values, I would have set all of the bits to 0. Because remember, AND is a bit selector, and basically what I'm saying is I want to select all of the bits except in the location where I plan on replacing a new value or setting a new value in. Okay. Now, once we've gotten that set up, we kind of have prepared that original bit string and it's primed to insert our new value. And then all I need to do is I need to take this string over here, my value string that I prepared earlier, and I just need to OR it against this string over here. Now by ORing it, and again, remember OR is a bit setter, I will end up setting all of the bits in that little chunk to correspond to what I originally intended on inserting. Now, if I hadn't kind of cleared out those bits originally, I would end up getting potentially extra 1s. So for example, if I had not done the step and I just ORed this value with the original string, I would end up of having that 1 still present, which obviously wouldn't have been right. I wanted a clean slate so I could OR in exactly what I wanted to in that location. Okay, so this is the first way of doing things. Again, if you're not sure, go through the example once or twice and write it out for yourself and see what's happening. These examples might kind of feel a bit odd, but you get used to this approach very, very quickly. So let's go through a different way of filling in a field. I personally feel this is the more intuitive of the two ways, but again, I'm biased. This may just be what I find more intuitive. It may not be the case for you. So again, we want to fill in a field, same as before, but we're going to do it using our new rotation operator that we got before. So what we're going to do is I'm going to start by rotating the register right k bits. This basically will get the lower order bit of the field I wish to replace as the lower order bit. But because I've rotated, I've not lost any data. All the lower order bits are just currently residing in the higher order bits. Then I'm going to shift right by m minus k plus 1 bit. So basically this is the size of that chunk I wanted to replace. And then they all fall off the cliff. So basically this wipes all of those bits that I no longer want because I intend on replacing them. Then I shift left by the same amount of space. So basically I'm just undoing that shift. And in the process, I'm adding all of those zeros in that location. Because remember, if I shift left, I induce zeros in the lower order bits. Then I just need to OR in my new value. And then lastly, I rotate the register left k bits, basically undoing this first step. So let's see this in the example. So exact same setup as before. We want to replace bits 3 through 6 with this bit string over here. Okay, so first thing is I rotate my original right by k. So basically the bits that I wish to replace are now right at the bottom. But you see that I didn't lose these lower order bits. They now just reside over here. Okay, so I didn't lose anything. Then I'm going to shift right by the size of the chunk. So in this case, it's of size 4, or you can obviously go back to calculation. 6 minus 3 plus 1 is 4. And now I will end up having what was over here right at the bottom. So basically this goes to the bottom. But now I just induce these higher order zeros, which aren't relevant at the moment, but it's just good to know that I didn't change anything. I just got these zeros. Then I undo that right shift with a left shift by the same size. And now I'm basically in the same position I was over here. The only difference is that now this field that I want to replace is all 0. And now you know from the previous example, we like having those bits set to 0 because they're primed to kind of be set using an OR operation. And that's exactly what we're going to do, is we're going to OR this bit string with the original value that we wish to insert. And again, OR is simply a bit setter. So now we end up with the bit string we want with those new bits inserted, that new field inserted. The only catch is that all the bits are right, they're just not in the right place because we performed that original rotate right. Okay, so to get it to this position over here, we perform that rotate right. So all we now have to do is we have to rotate left by the same amount, and then we move the bits back to the correct location. And now you'll see that what we have at the end here is exactly what we started with over here, just with the correct new field inserted. Now, I personally find this easier, but you may find the other approach easier. But you should know and understand why both work, because sometimes the tricks that were used in the other approach are more appropriate to solve different kind of problems than this approach. But it's good to always know or be able to do both. Now, there's one last thing I want to quickly discuss, and this is the idea of bit testing and setting. Now, everything we've discussed really up until now has worked on whole bit sequences or bit strings. And while we could actually extract singular bits using these kind of approaches, we can do it more efficiently than just that. We have in assembler an ability to test specific bits directly. So let's go through how to do that. So we have basically 4 instructions that are relevant, at least to this course, that do this bit checking. They're called BT, BTS, BTR, and BTC. And the way they work is as follows. We pass through 2 operands. So we'll have something like BT, say a register, and then which bit we want to look at. So say I want to look at bit 13. Now, what will happen is if the bit, the 13th bit, so index 13, of RAX is true, we will end up setting the carry flag to be true. Now remember from before, some addition and those kind of operations would set carry flags. Same thing applies here, just we're explicitly setting the carry flag to basically be 1 if the 13th bit of RAX was 1. Now it's great and well that we've set the carry flag, but how do we gain access to it? So the way in which you can gain access to the carry flag is simply using setC followed by an 8-bit register. So in this case, the most common is just to use CL. So you go setC, CL, and it will set this register to be the bit. So it will be 1 if the 13th bit of RAX, or index 13 rather, is 1. And if the 13th index of RAX is 0, then CL will end up being 0. Okay. Now, these other 3 versions are kind of tweaks on that original idea. This BT simply does what's called a bit test. And then we have a BTS, which tests what the bit is, exactly the same as we have over here, and will store the result in the carry flag, but it also sets that bit to 1. So it does 2 things. It does a test and a set. So that's what the T and the S stand for, test and set. Now, sometimes you may only be interested in setting the value and you don't really care about checking it, and that's fine. You can still use BTS because it will set the carry flag, but if it's not relevant to you, it's not a problem. You're still able to set the bit that you want it to, and in this case, it will set it to 1. Okay, so it doesn't take another parameter to say you want to set it to 0 or set it to 1. Set means put on in this case. We then have BTR, which stands for bit test and reset. This will also store the result of the bit you're looking at in the carry flag, and it will set it to be 0. So that's why we said reset it. It blanks it out. It will set that bit to 0. And then the last one, which you probably won't find too much use for in this course, but I want you to kind of have a more complete picture, is BTC, which stands for bit test and complement. So again, it does the test, stores the result in the carry flag, but it will flip that actual bit that you were looking at. So if it was a 0, it becomes a 1, and if it was a 1, it becomes a 0. Now, all of those operands, all of these instructions take 2 operands, and the first one is either a register or a memory location, and the second one is, generally speaking, an immediate value, or you can use an 8-bit register. For most examples, for us, simply using an immediate value will be perfectly fine. So let's look at 2 quick examples of using this bit test functionality. It's quite a bit more straightforward than I think those fill and replace examples we just discussed, but the first is let's check if a number is odd. You'll remember that we showed you earlier how to make a number odd, so now let's check if an arbitrary number was odd. So say we want to check whatever is in RAX, so for this example I just loaded in 101, and all you have to do is you have to go BT for bit test, the register and the bit. So in this case we want to check the lowest order bit, which is bit 0, and the result will be stored in the carry flag. Now I want to extract what was stored in the carry flag, so I simply use setL followed by an 8-bit register. I'm just using DL for this example. And just as a note, it has to be an 8-bit register. You can't go setC and then use a 32-bit register. The assembler will not allow you to do it. So I use setC DL, and then whatever the lower order bit was will be stored in DL. Okay, and in this situation it will be a 1 because obviously this was an odd number. And then we can do a comparison off of that. We can do further tests. So when we get to proper if statements in the next lecture, you'll see that I could say, well, if DL was 0, do something. And I can decide based on that. So this is how we could check if a number is odd. We can also obviously use this approach to directly set bits. So say I wanted to set the 7th and the 33rd bit of a quad word. That's in memory to 1. All I'd have to do is go BTS for bit test and set, specify where in memory and what value. Now again, if I was doing this on a register, I could simply go BTS, RAX, and then I could, for example, say 7, and that would set the 7th bit to 0. But because in this example over here, and I repeatedly say this because it is a place that I find students often forget, if I had something like BTS A7, again, it's ambiguous how big this memory is. Okay, so it's why we're forced to specify the size. So in this case, if A was a quad word, I have to use QWord. Okay. And that brings us to the end of this section. As we go into the next section assembly, you'll start seeing more interesting things like conditionals and loops, and we can start kind of building full-fledged programs in assembler at that point.